Hello everyone, welcome to the 5th webinar of our Microseismic in Geomechanics webinar series. Today's speaker is Dr. Philip Usher. Phil is a software developer with a strong background in geophysics. He is primarily involved in the development of InSight application, advanced microseismic data processing, and also provide technical support to InSight users here at IMaGE. Phil has a PhD in geology and a master in geophysics. So, Phil, please take it away.
Thanks, John Wayne. I'm Philip, and I'm here to talk about data interpretation, particularly recognizing biases in our data. And so how I'm going to do that is I'm going to, there we go, I'm going to talk about interpretation and bias. I'm going to look at causes of bias, what will affect our data. So we have detection limits, we have effects of noise, radiation patterns, and location uncertainty all cause problems with our data. And so to deal with that, we can do a certain amount of data selection, so picking up the best bits of our data. Once we have our best data, our data with the highest quality, we can then interpret the data. We can look at that with pumping data, or we can interpret the data in space. So the idea of making a fracture box or an isosurface. Finally, we can look at how to integrate our data within a geomechanical framework. And I'll end the slide with some conclusions about what we've done. So this webinar fits in with our webinar series. We've had numerous previous webinars talking about survey design, data triggering, classification, data QC, and fitting these in. So this gives us our microseismic data set, hopefully with a lot of the data with high quality. And so, however, there's always going to be some biases left, some errors, some some problems with the data that we need to be aware of. And so if you start with bias, you're going to end up, if you start with biased data, you're going to bias your interpretation. And we need to try and find a way of unbiasing our data, try and get out as much as we can. If we had perfect unbiased data, we could then have a perfect interpretation. But the problem is we're probably going to be somewhere in the middle and looking at, having to deal with some biases and make sure we know about them and make sure it's communicated clearly. So the first effect is a detection limit. And what happens is that things can affect the microseismic amplitude, such as the magnitude, geometrical spreading, scattering, and inelastic attenuation. So the geometrical spreading is the idea that you may have seen these ripples in ponds, and this picture is often used in seismic to help explain. You have a sort of a large amplitude in the middle, but as it spreads out with each wave, it has to spread out over a greater area. So as the circles get wider, the amplitude gets lower. This is the same in microseismics, except it's in a sphere. It's in a spherical, expanding wave, and so you end up with less energy that way, and thus small amplitudes. And then you also get scattering. So if we have a ray traveling here from left to right, heterogeneities and changes in the rock can cause the energy to be scattered in different directions and out of our ray path. And that means we end up with, again, less small amplitudes. There's other such effects, such as inelastic attenuation, so if it heats up the ground subtly or moves fluids about, you end up with a loss of these amplitudes. And these three main things, geometrical spreading, scattering, and inelastic attenuation, are all functions of distance. As you go through more rock, the effect becomes greater. And so we end up with smaller amplitudes for vents that are further away, even if their magnitude is the same. And this can be shown in a distance versus magnitude plot. And this is one of our first plots to look at when trying to look at our detection limit. Basically, our detection limit is this line here, where we end up with, we can see events, we can see smaller events, smaller magnitude events at smaller distances. So this is distance versus magnitude, and as you get further away, you can only see the higher magnitude events. At some certain distance, there would just be a sort of minimum magnitude that's detectable, and this is due to sources of noise that are always going to overcome no matter how close you are. Now, there's numerous sources of noise. Some are natural, such as wind, oceans, or tidal forces. Quite a lot of anthropogenic, man-made sources such as drilling, traffic, if you've got surface sensors, generators, pumping equipment, generally making anything that's making sort of vibrations can cause a sort of noise. And if you get any vibrations in the monitoring well, you also get, there's always some level as well of sort of electrical noise from sensors and the recording equipment. And what's interesting is that these noises can also change through time. So if you end up, sometimes the generator's switched on, sometimes it gets switched off, and you're going to end up with different noises at different times. Even on some examples, it's been known that as you frack towards your monitoring well, the frack has actually entered, the fluid has been entered into the monitoring well. And that's what's shown in this graph here. You've got the RMS noise here with this grey line. It suddenly jumps up at this location, and there's a small drop in the slurry rate at this point. And this is as the fracture entered the well, caused a lot more, caused an increase in noise. So after this time period than before. And you can imagine you're going to get a very different earthquake catalogue, different microseismic catalogue before and after this, as the noise level has changed significantly. Something else that can affect our microseismic catalogue is the radiation pattern. So vast majority of earthquake sources in microseismic data are normally these double couple strikes at faults. But actually, other systems do have these nodal planes, where the amplitudes are very low. So you can hear we've got the fault plane, you've got very high positive amplitude, very high negative amplitude, and in the middle it has to switch, and so you can imagine that there's a direction around the focal sphere of zero energy, zero amplitude, and this can be shown in a sort of map view. If we have most events with majority the same focal mechanism, eventually you end up in a direction where you're in a focal, you're in a nodal plane, and that's going to cause drop in amplitudes and thus a drop in detectability at that point. Something else that will affect our interpretation is our knowledge of the uncertainty, particularly location uncertainty. So although we've maybe quality QC'd our velocity model and we think we're at the best we possibly can, there's always going to be some error, some variation in this velocity model that could be accounted for. Similarly with picking, no matter how many observers you have looking at it, refining your picks to the best quality, there's always going to be some error. Some are going to be small, associated with the difference between the exact onset of the wave. Some could be larger if you misidentified a phase and other such problems. And this location error, so this uncertainty is going to cause us problems in our data set. This is an example where we've got a monitoring well up here, a treatment well, treatment well here, monitoring well to the left, and we've got a fracture cloud coming out from here. And you can see it's wider near the treatment well than it is further away. Now, a naive interpretation might be that this is due to the actual fracture is wider here than it is further away. But if you plot the errors, so these are ellipses representing the error and the location, you can see the error is going to increase with distance away from the monitoring well. And so what we might be seeing here is this increase in scatter is actually an increase in our, is actually due to an increase in our location error. So it's likely that the fracture is probably not changing, or not measurably changing in width along these distances. It's just an artifact of our location uncertainty increasing. So how can we look at that? Well, within Insight, we can do a Monte Carlo analysis. This involves, what we do is we change, we take an event location in the middle here. We then can subtly change the arrival times, the source vector, and the velocity model. And we try this 100 times, subtly changing each of those randomly within a limit. And you can see how it's going to scatter our location. So we get a measure of what our scatter would be. This is maybe an overestimate, but you can see that at least with our monitoring well over here, we get an ellipse that's sort of in line with that. And you can see that, so maybe measuring again this fracture width here might be difficult to constrain, but we know that we're probably pretty, this direction could be much better, as that's got a smaller location error in that direction. So what we can do about these these biases is we can try and make sure we select data that is missing and has full completion. So again, this is our moment magnitude versus distance plot, but for a different data set. And you can see that sort of above, so 0.6, maybe above 0.4, we're going to have a mostly complete data set, as we have, so that's where our magnitudes are complete. Whereas these events down here, you can see that there isn't, we're never going to pick a minus 0.8 event at 600 feet away. So, those events are never going to be, aren't going to be seen across our monitoring study. So we can see this effect on the sampling here. We have a monitoring array and injection at depth here. And you see that it's quick. If we filter out these low magnitude events, we can filter out the some of these events that are nearer the well. And we end up with a more, we know that there's some events around, and what that suggests is that even though this event, it looks kind of lopsided, it looks like the fracture is propagated much more on the western side than the eastern side. That's actually an effect of our bias. And if we remove that effect, we know there's going to be some extra events around these. So we have a good quality set in the middle. You can also look at filtering the data based on RMS location error. So if you have RMS location and it suddenly drops, you can see that, well, these events have got spuriously large errors, and we can get rid of those and try and reduce again to gain a higher quality data set. So once we've filtered our data to get the best quality events, then we can look at interpreting them. One of the first things we look at is an interpretation of pumping data. So this is looking at pressure within the well with this red line. We can look at flow rate as the blue line, proppant concentration as the green line, and compare that to some indicator of microseismic events. So the sort of event rate or histogram of bins. You can plot this over the same time period, and you see that we end up with different comparisons of rate to the same injection. So if you have, say, a lot of events at the beginning, we've got a lot of microseismicity due to the initiation of the fractures that they're starting, breaking up the rock. If their microseismic events are focused near the end, then we're probably getting proppant screen out, where the proppant's blocking up the fracture and causing increase in fractures, increase in microseismicity. And then, if we want uniform fracture, then we'd expect. So we can learn about how our fractures are progressing with time. It's also good to look at how our fracture is in space. So one thing that Insight can do, it can fit a box around our events. This is quite a sort of simple method looking at just fitting the best box around the events. And you can see that if we use the filtered data, so if we remove these near events, we can end up with a sort of smaller estimate. However, if we use the whole, we can end up with a, however, if we use the unfiltered data, we can end up with a larger estimate. So, each of these overestimates and underestimates have got different effects that can happen. So events can be caused due to stress arching. So by not necessarily being the fluid connected fracture. So as you input, a fracture in a rock, it's going to change its volume, and that will cause earthquakes, away from the fracture, and those could be measured. We're also going to get things like the location error causes this scatter on the events, and so that could again be making our box be too big. But there is other effects out in the other way. So if we've got little events, as we see here, they may be missing from around. So it could be that our detection limit is causing us to not see some events that we should see. Insight can also look at doing using an ISO surface, so sort of fitting again sort of a cloud around this to see what sort of volume is stimulated. But here we may be sort of overfitting the events. So sort of a lot of this location error and stuff is due to a lot of the location error gives this scatter. So you're never gonna know, are we just missing a few more events here, which is why this chunk's missing, or is that an actual artifact? So we've got to bear these different numbers in mind, the different ranges of fracture volumes that can be created. A better way of looking at the microseismic data is to go into using a geomechanical interpretation. So this way, instead of looking at fracture volumes, stimulated reservoir volume areas, things like that, you can look at using a discrete fracture network, so a set of series of planes, a set of input stresses, and run those through a geomechanical model. So input our pressures and stuff from the well, and see how the network would react. See what microseismic this would create, predict, and then compare that to the measurements, and then rerun to see how our important economical measures such as our permeability and such are affected by these different models, and compare that to our microseismicity. However, I don't want to go into too much detail on this, as there will be a later presentation based on that. In conclusion, we've got a set of biases causes problems in how to interpret the data. Causes of this bias include things like the detection limit, noise, and location error. Data selection can limit the effect of the bias on the interpretation. So if we select the best quality data, we can look at the highest quality interpretation. But most biases can be mitigated by this, and you need to be taken account into the interpretation of the variations in values. So these fracture volumes need to be carefully communicated to make sure they have value, just to make sure that you understand the range it needs. And so ideally, microseismic data should be used to enhance the geomechanical model. This way it can be used more robustly. So that's it for me. We'll have some more webinars coming up in September. We're going to be looking at induced seismicity, so looking at safety and causes of larger microseismic events, and how we can maintain our operational licenses. Then in October, there's going to be a talk on microseismic geomechanics, so again looking at this interpretation and how to best use our microseismics with more advanced models. And then finally, there'll be a webinar on acoustic emissions, so looking at lab data. If anyone has any questions, please write them down in the chat, and we can I can see if I can answer them. show up meandering way, happy to answer anything. Thank you.